Okay, so here are the functions he derived. So this was the, did he call this the first or second order approximation?
I think he called it the first one.
Okay, so this is g of x is the one that preserves the derivative, and h of x is the one that preserves the first derivative and the second derivative. So we start with e to the x for x greater than 0, and then so here's what the reflection looks like for the first order. So I'm plotting g of x here. So tell me what you think about this as a reflection.
So I mean, it kind of looks like a reflection. Like this part looks like it's curving down a bit steeper than this is going up. But if I just looked at this without reading the article, I wouldn't think that the positive half and the negative half were reflections of each other.
You wouldn't have used the word reflection here. Okay.
They look related, but I wouldn't have said they were reflections.
Would you have thought that this left half over here related to e to the x, or was it some sort of exponential function?
It looks exponential. I mean, if you let it continue, it looks like it's getting steeper down, and this is getting steeper up. It looks vaguely exponential.
Okay. What property does it have that an exponential function definitely does not have?
It's negative.
It's negative. It crosses the origin. Okay, so let's look at h of x. Just to... Alright.
So this doesn't even look like an exponential anymore. It looks like a parabola. If you like made this go a little further this way.
Okay, so we can do that pretty easily. Let's go to -2. There you go.
Now it looks a bit different, but it doesn't seem to resemble anything related to an exponential function, because it does go up steeply here, but then it goes down and comes back up. And this one, if you go at it from this side, you have e to the x still here, and then you go down to 0, and then you go up.
Yeah, it's not quite 0 if you look at the scaling.
Very close to, or just a small value, I guess.
Yeah, let's go from -1 to 0. I don't think that is 0. Yeah, so it's 0.9, 0.8, so it's, a little bit below 0.7, but you're right, it definitely has a minimum. Definitely has a minimum.
Most exponentials don't have.
So I'll go back to plotting it from -1 to 1. Why don't you pick another function rather than e to the x? Maybe while you're thinking of that, we'll go back to the first order approximation. Okay. So what would you like to do? You can pick anything you want.
Let's do sine x.
Okay. And before you hit return on this, what do you think qualitatively that this is gonna look like?
Well, I mean, we're only going from -1 to 1, so a reflection. You might have the normal sine wave over here, and then you maybe have a sort of distorted sine wave on this side.
Okay. What does sine x look like near x equals 0?
It looks like x.
Okay.
So.
Alright, so here we go.
Yeah, so I guess it's not, we're zoomed in enough that you can't really see the individual waves.
Okay, so what would you like to make the limits go to?
Maybe minus pi to pi.
Minus pi to pi, okay.
So yeah, this is our nominal wave, and then this kind of looks like a bit of a parabola here. It's not coming back down.
Well, maybe we can zoom way out. How about go from -20 to 20? Let's see what it looks like there.
Alright. It's interesting. It almost looks like, and we've looked at like composite trig functions before. This side looks like that. I guess that maybe is to be expected because we are kind of adding signs together.
Yeah. Yeah, it's just a different wave on the other side, which is kind of cool. Why don't you pick one other function and we'll see what the reflections. Actually, we should I guess do the higher order one first, right?
Yeah.
See how that changes it. Oh.
I guess it's just more varied now.
Yeah, maybe if I go from -40 to 40, maybe it'll set the scale right. Yeah, there you go.
It still looks like it's overall the same shape, which is kind of cool. You have this a big wave up, big wave down, then a smaller wave, and then a bigger wave.
Yeah. Cool. All right, so pick another function and we'll look at it.
How about let's do like a cubic or something.
Okay.
Just do x. Oops. Cubed.
Okay. Yeah, let's do from, well, let's not go from minus 40 to 40 if we're looking at x cubed. How about minus 3 to 3? And let's look at the
G of x.
Okay.
So this still looks like a pretty good inverse, or not inverse, or reflection, but it, again, like the e to the x one, it's going down faster than the original function is going up.
Yeah, interesting. Maybe if we go from minus 5 to 5, we'll see. Looks about the same. Okay.
Yeah, it looks like it's going down roughly 3 times as fast as it's going up.
Yeah, interesting observation. Yeah, sort of at every scale it kind of looks the same. Now, so that preserves just the first derivative. And what is the first derivative of x cubed at 0?
It's just 3x squared at 0, so just 0.
Yeah. And then here's h of x. Ah, okay, so this is very different.
Yeah, so it's not going down anymore. It's it almost looks like a 4th degree.
Yeah.
Where it's kind of flat around 0.
Right, it doesn't look cubic anymore. So it's interesting. So these are different types of reflections. Okay, so now what we'll do is we'll try to derive a formula for when we use something different than x over 2. And then maybe we can compare just the first order approximations and what they look like.